Right. Perfect. So my name is Zach Shwerapkonti, and I'm a research associate. Rather, I'm a Turing Research Fellow at the Alan Turing Institute here in London. I would also like to introduce my colleague and co-organizer of the seminar series, Andrea Pizzaferato, who is a visiting academic at the Alan Turing Institute. And for those of you who are not familiar with this institute, this is UK's National Institute for Data Science and AI. Also, on a side note, if you are interested in sharing your work in any of our upcoming seminars, please do get in touch with either Andrea or myself. And as for the format of the seminar, our speaker for today will talk for around 45 minutes, followed by Q&A session, which may be done through the Q&A feature in the Zoom window. So without further ado, I'd like to ask Andrea to introduce our speaker for today. And with that, I thank you all.
Okay, thank you, Zach. So our speaker today, Morten, is the group leader and professor in the Department of Chemistry and Bioscience at the Aalborg University in Denmark. He received his PhD degree in material chemistry from the same university in 2011 and worked as a research scientist at Corning from 2011 to 2012. His current research focuses on the structure and mechanical properties of disordered materials. Morten has 10 patent applications, 5 granted, and over 200 journal articles. He received a ERC Consolidator grant in 2022 and is a fellow of the Danish Academy of the Technical Sciences and Danish Academy of Natural Sciences. His awards include Vittorio Gottardi Prize, Sir Alastair Pilkington Award, Grundhof Prize, and Best PhD Award from the Danish Academy of Natural Sciences. Today, he's going to talk about interactions between the glassy states of disordered system and material science. So thank you again, Morten, and without further ado, the floor is yours.
Yeah, thank you very much, Andrea. Thank you for the kind invitation and presentation. So I guess, do you see my slides full screen now? Great. Okay, yeah, thank you. So so my background is actually trained as a chemical engineer, now more doing material chemistry, materials engineering. And of course, as the focus today in interest and using different types of methods from data analysis, machine learning, coupled with understanding of chemistry and physics to make glasses better, essentially. So I will give you, of course, first some background of the basics of glass, what types of problems we're trying to handle, and some examples of our research where we apply some of these approaches from data science, machine learning to, most of our work is around, as Andrea mentioned, about mechanical properties of glasses to make them stronger, to make them tougher. So I'm our group is situated up here in Aalborg in northern Denmark, the happiest city of Europe, at least according to ourselves. And as I said, so we're interested in glass materials, and for us, as I'll kind of argue and explain to you, if you're not familiar, so glass is much more than just the typical types of daily glasses. It's a state of matter and a wide range of materials that we're interested in across different time scales, across different length scales. So last year we had, as you may be aware, we had the UN International Year of Glass. So the United Nations typically have one or more topics that are celebrated every year, and last year was the Year of Glass, for the key role that glass has played and continues to play for modern civilization and scientific discovery. So just to mention some of these. So of course, architectural glasses we know very well. We also look glass to look at some of the biggest things and some of the smaller things that we know. But also, if we look ahead and already now, of course, there are many applications where you may not think that glass is playing a critical role, but it actually it is. So, for example, something like energy, also something where we have several research activities. We use glasses for wind power, glass strong, stiff, I should say, and lightweight glass fibers are very important for solar applications. As well as for battery materials, more emerging application like for solid state electrolytes, which I'll also come back to a little bit. For some pharmaceutical packaging, glasses are also very important. And the key point I want to make is that for most of these applications, the type of glass that is used is not the same. Of course, in some of them, architectural windows, it's the basic types of soda lime silicate glasses, but for many of these, the individual glasses is engineered and designed for that particular applications. Okay, so then what is a glass? So even us in the field not always fully agree about the definitions, even though it's this very old material. So this is a definition from 2017 that I like from good collaborators and colleagues, Edgar Sanotto and John Morrow, saying that glass is a non-equilibrium, non-crystalline condensed state of matter that exhibits a glass transition, and the structure of glasses is similar to that of their parent supercooled liquid, and they'll relax to this state, and ultimate fate of is to crystallize. So if we look at this and try to translate this, if we look at this in terms of enthalpy and temperature, this is a typical diagram to understand glass formation. Then if I have my raw materials, so the typical ones would be sand, soda, and limestone, we heat them up and we form the liquid state. If we cool down this liquid slow enough, then we can get a crystallization, phase transition to this crystalline state. If we cool the same liquid relatively faster, so it doesn't have enough time to crystallize, we form this supercooled liquid state that becomes increasingly viscous as we cool it down, and at some point it freezes in on that time scale, and we form this glassy state. Excuse me, this non-crystalline state that will then can relax and then can crystallize. So you may also have heard about amorphous solids. They are not the same. So amorphous materials both also have this non-crystalline structure, but the glasses have this glass transition because of the way that they are formed. Yeah, so some scientific differences there in terms of those terms. So a video here from our lab, from some of our students, of how we make glasses in the lab, very much similar to how it's made on large scale. So we have these liquids. As I show you, we cool them down, as you can see here, when it changes the color. And we have our beautiful glass state that we can then do further processing and engineering of. And of course, for most of the composition, they will all be transparent, but the chemistry of this is what we are interested in and what our group is interested in. Okay, so to tailor glasses with some properties, of course, in material science, the paradigm is, of course, we need to understand the structure. And the structure kind of glass have, of course, it's much more difficult compared to, at least traditionally, compared to many crystalline materials, because we don't have the order. We have this disorder, this amorphous state, because of the way it's formed. And the study really started from this brilliant paper by Zachariasen in 1932 at the age of 26. Yeah, with this statement here, and of course we know more today than at that point. That's for sure true, but still a lot of things to understand and to analyze, and that's where we think some of these physics-informed, for example, machine learning methods can be very helpful. So this is TM image of a 2D film of silica, amorphous silica, glassy silica. Sorry, that's found here. Yeah, and as I said, glasses, so it's the state of matter, so we can find glasses across a variety of different chemical families, organic, inorganic, non-metallic, metallic, and some hybrids. Yeah, and of course, the traditional glasses that we talk about when we say glass in daily life would be these oxide glasses. And that will be the main focus of my talk as well today. So when I say glass, I will be referring to these oxides, but just keep in mind that there are a variety of different material families that actually form or can form this glass state, and have of course differences according to the chemistry, but also have similarities just because they share the underlying features of the non-crystallinity, the non-equilibrium nature, and so on. Okay, so glasses are disordered, while crystals are ordered. But what I'll argue and explain to you is really it's a matter of the length scale. So of course, in crystals, we have the repeating units that form this long-range order. But in a glass, we typically, or we will have the so-called short-range order, so that a given atom will have the similar type of nature, or sorry, similar types of atoms as neighbors, different places in this structure. We can also find similarities in the types of rings. There'll be distribution of these rings, but there will be some ring sizes that are more likely to show up than others, and that kind of beyond this first coordination shell we'll call medium range order. So they are disordered, but we do find some order at different length scales. And of course, this is very helpful for us as engineers, material engineers, to try and design these materials with some improved properties. So just to show you a little bit of the chemistry, so the types of structures that we could be looking at, typical elements that form these glasses could be silica, so of course from sand, boron oxide, germanium oxide, that kind of form the backbones of these networks, these glass networks. Then we connect them and we form this structure as I showed you. So something like this is pure SiO2 forms a nice glass. It's a nice glass former, but the temperature to melt this is very high. So we could make this, and this would actually also make for nice products, at least used in some applications. But the melting point of this very connected network is very, very high. So as has been done for hundreds of years, we modify the structures of these materials, or something like silica. So we have what we call network modifiers. These are elements that are bonded much more weakly, typically ionic bonding in the network, that breaks up of some of these more covalent type bonds in the structure and and lower the melting points, and of course also affect other properties. Some in a good way, something that we like, and others in a way that is maybe not so favorable. But we need to do it to be able to melt them. And this is also where kind of both the good and the bad of working as a glass chemist comes in, because we can really tune the structure, and we can tune the structure by different elements from the periodic table. And we are not limited by a certain crystal stoichiometry. So the number of possible ways that we can form these glasses is tremendously high. You can, of course, count this in different ways. If you take some of the typical elements that are not too toxic, not radioactive, and so on, you vary each of them by 1%, you can end up with a number like this. The exact what the number is, maybe not so important, but just to say it's enormous. And of course, this is also where machine learning comes in and becomes very helpful. Because to believe that today we have already come up with the best glasses for a given application is very unlikely, considering all these numerous possible compositions. Of course, with a lot of restrictions in terms of availability of the raw material, in terms of price and so on. But even putting all these constraints, there is a huge number of compositions because of the nature of glasses. So what do these modifiers do that gives rise to these possibilities, but also, yeah, as I said, modify the structure? So again, it's complex because it depends on what type of former that is building the network. In these typical silicate glasses, they will break up the network and form these weakly connected bonds. In other types like borates, actually, they will first increase the conductivity and then start to decrease the conductivity. And in other systems, actually, there is still not a very detailed understanding, at least not in all compositions, about what is going on. So the structure is being modified in different ways, some ways that we know, and others ways where we still have some unclarity. And they are all not just always randomly distributed. They can also be ordering in terms of clustering of some of these elements in the networks, making it complicated. So coming to the first kind of example of what we have been doing, so to try to predict these short-range structures, so these coordination states of the glasses. So this is an illustration. This was original work by John Morrow. Here looking at different of these network formers, so like aluminum, silicon, and boron. And then when I add a modifier, one of these elements could be a sodium, a lithium, calcium ion to my glass. As I explained, they will interact with some of these network formers. But which one will they interact with? Will they interact with the silicon, the boron, and aluminum? or is it just all random? And that's what we've been trying to figure out and trying to predict that, because of course, which of them they interact with will determine what structure we get of the glass, and therefore what properties comes out of it. And we were using some type of statistical mechanics to predict these interactions, partly data driven, and understand these interactions and comparing them with structural data, experimental structure data. And in simple systems, so this is another network formula, this P2O5, so phosphorus oxide, adding some modifier, and then this is some names of different structural groups. And we can see the experimental points, and data prediction works quite well. And with these parameters of interactions between the formers and the modifiers, we can predict this quite nicely for some simple systems. Then the problem comes when we go to more complex systems, when I need to start to combine different types of structures with a variety of different elements that interact. And I need to take my parameters from the simple systems to the more complicated systems. And then, I mean, we would have to do a lot. So then, of course, what we tried was instead to use machine learning, just typical neural networks, to just look at the composition structure data sets. But as many cases, of course, it works well for interpolation, but not very well for extrapolations. So instead, what we tried to do was to train the machine learning model not only on the purely the experimental data, but actually on these lines here, these mechanically calculated lines, to learn them these interaction laws or parameters that we can get from these. And in that way, we show that we could get much better extrapolations of the structures. These are some experiments in measures, some predicted ones, not seen by the model. So by letting the machine learning model, learn the thermodynamics of these interactions, we get a combined model that both can cover a variety of different compositions that would be difficult with the purely physics or statistical mechanics based model, and still allows for the types of extrapolations, at least in what we tested here, pretty well in what we've tried so far. So that was the kind of the short range of the structure. We're also interested in these the more medium range structure, and so that was, for example, these ring structures, these voids. So here it becomes complicated because we're not even sure what's the best way to really to quantify and to classify these ring structures. So we've been working with a mathematician. This is Lisbeth Feistok, one colleague, applied mathematician here from Aalborg, in trying to use something called topological data analysis. So it's not machine learning, but it's topological data analysis, or a tool of that is so-called persistent homology. So what it does is that it's used to find shapes of data. So we have some input points, and in our case, this will be looking at atomic positions of so each point here is an atom. We look at the positions of that we could get from simulations or from experimental data combined with some so-called reverse Monte Carlo modeling. We get the positions, and then the idea of this persistent homology is that you let the atoms grow, and you start seeing these shapes, these here the ring appearing when they are all when they start to intersect. We see when they grow further, we see this other ring up here, Y, forming, and then when you grow them further, it will disappear, and later this X loop that we formed over here will also disappear when they have grown sufficiently larger. And this gives rise, and this is called in this field, it's called death and birth of these different features here. Rings, it could also be voids or holes that we are enclosing with the same concept. And you get these so-called persistent diagrams from these. And what it turns out is that you can actually, with this, you can capture the types of structures that you get in the glass. You get both the types that are chemically bonded, typical ring structures, but also structures that are not apparent to us with our typical chemical understanding of what are some repeating structures. So also units that are found around the structure, but it's kind of a hidden order, something that we don't see as obvious. So this is work from not from our group, from Hirooka, looking at this for crystal, liquid, and glassy forms of silica. and seeing the different these persistent diagrams. So again, these death birth diagrams. Of course, there's nothing down here. There's nothing that these loops do not die before they are born. But then in the crystal, you can see that we have very well-defined regions of these loops that form. In the liquid, everything is fully disordered, still very disordered in the glass, but you find some more regions or spaces where we don't have points. And then, of course, we can go in, we can find representatives for that and look at how that looks like in the glass structure. So what we can show, and I don't have time to go into all the details here, but what we can show is that this can actually be related to also experimental structure data in these types of materials. To understand this disorder, we can classify these types of diagrams according to, for example, the number of atoms that are in them. And as I said, we can correlate that with the experimental simulated structure of these materials and find these types of ring units of medium range features that describe these behaviors. And you can also imagine you could use this, of course, these types of features, and this is still something ongoing work, to extract these types of features and use these as well as input for machine learning models to look at properties here with thermal conductivity for some samples at these features. And then the good thing is that we can, with our physical understanding of this, we can go back and then we can see for a given prediction property, because we can do this in different dimensions. We can look at distances, rings, and voids, and see what is the relative contributions of these features to some of the glass material properties. So we've been doing a little bit of that, but I still think there's a lot to be done in this field, and understanding kind of the advantages and also the limitations that for sure are also there with this type of approach of using this topological data analysis. Okay. So that was structure. So what we have been trying to do with structure at different length scales. So we're not just interested, again, as a material engineer, not just interested in structure just for the purpose of structure, because we want to use it for making better glasses. So as very well known from daily life, so glass still breaks, and these are brittle materials. And of course, our research dream is to break these limitations and to make things that we can at least to some extent bend and can have what we call plastic deformations to open up new product categories. So glasses break because stresses typically amplify at the presence of defects. So we have surface flaws and amplify the stresses, and because we don't have stable shearing mechanisms, no permanent deformation, then we have catastrophic fracture. So we know that we drop a piece of glass and we can take up all the small pieces and we can put them perfectly back together because no permanent deformation had occurred. And we also know from daily life that we drop a phone, for example, that it may not break the first or the second time, or then maybe a third or fourth time you drop the phone even from a lower height, it may fracture at that point, even though the applied stress from the impact was not maybe lower than the previous ones, but because you have accumulated these surface flaws and they become large and they amplify the stress more, and you can have the fracture, the brittle fracture from that. So of course we want to understand this and we want to design these structures to have improved performance. So why do we want that? So of course, mechanical performance has always been critical, but now it's big. I mean, I guess like other properties, but there is coming higher and higher demands. So there's more widespread use of glass products. There are in other types of applications. Of course, glass has also played a big role during pandemic for distributing the vaccines in these glass vials here. And the safety requirements for these types of glass is you don't want to have small chips in the medicine or in the vaccine for the liquid, for example. So these are very large. We want to there's upscaling to larger pieces of glass. There's emerging applications where there are higher requirements. And then, I mean, maybe the most important one is that, of course, we want to lower the CO2 footprint of glass manufacturing. And the most efficient way of doing that is to make thinner glasses for those that we use today. So that affects the whole chain, because glass production is a very CO2 intensive process, high temperatures, also carbonated raw materials in many cases. So if we can make them stronger, if we can make glasses tougher, that is really the key step to making them thinner, and therefore reduce cost or CO2 footprints of the production, of the transportation, and essentially of all the steps of those that contribute to that footprint. Yeah, so this was the example I had from before. So these numbers may be a bit outdated, but this is really a big course of concerns, of course, but also in terms of sustainability. If we can affect it, that would be a big thing. So glasses have actually, for those type of specialty applications, have become significantly thinner nowadays, and that, of course, have these beneficial sides that we just discussed, but it also puts higher and higher demands on these fracture properties that we are looking at. Okay, so it's kind of the motivation and background for our interest, engineering interest in trying to engineer these stronger, tougher glasses. So some example of what we've been doing. So coming from the structure that I just shown you, we can calculate different things. So we can calculate how rigid some of these bonds are, both in terms of what we call a radial constraints, so bond stretching here, or an angular bond bending like over here. So some of these will have large fluctuations around the mean value, both in terms of a bond stretching or a bond bending, and others will be much more constrained. They have less excursions around the mean value, and we can use that, or we can understand that from structure and from simulations. And then we have been using this to kind of connect that with material properties, with mechanical properties of some of these types of structures here, like the hardness, the toughness, the Young's modulus, and other mechanical properties that we can connect this understanding to the mechanical properties. And again, similar like with the structure, these type of approaches work pretty well when we are in simple systems, but to engineer these glasses, I mean, we typically don't only have these 2, 3, 4 component systems that we often like to work at in academia. We can have, can often be multi-component systems with maybe 5, 6 or more elements. Of course, making these types of models challenging, because you need to really know the details of each of these. So of course, there's again an interest in using more data-driven approaches. But if we, and I'll come to that in a moment, but then when we have this understanding, we can also show that we can actually use this structural understanding to design glasses with improved performance. Here, it's related to how some of these structural units change their structure, the glasses change their structure under stress, under pressure. And we can show that when they have a large change in that, they have a better mechanical performance. And this concept have actually also been, or is being used to design real industrial glasses. But as I said, how do we do that when we come to these complex systems? So this is recent work done with Anup Kristan's group at IIT Delhi. So here we were looking at glass hardness. So hardness is something that you measure by indentation. So we take this diamond tip over here, we apply some load to it, some P, and then we measure some and press it into the surface of the glass. We unload, and then we see some indent here, and we can measure the size of this indent here. And of course, the bigger this indent is, the softer the material is, the softer the glass is. But what makes this more complicated is that, of course, we take the load into account when we do the calculation of this. But even when on the geometry of this, you'll find that as we increase this load here, so as the indent becoming bigger, the hardness is decreasing, and there's different proposed origins for why and how that is. And and that's called, but kind of what it's called is called the indentation size effect. So we have this decrease here. And this becomes important when we want to try and predict hardness. So here, Anoop's groups was looking at 3,000 glasses from the literature, and trying to predict this composition and load dependence of hardness. And Vickers is just the type of shape here of the indenter here. So measured and predicted hardness for something where you don't take the load into account and something where you take the load into account. So from these data sets, most studies in the literature will report the load, but most of them will also just report one load value, the one that it was done at. But you can see if you train the model besides the composition, but also use load as an input feature, we get slightly somewhat an improvement in the prediction accuracy here. But of course, with still a lot of variation. And this even becomes more critical if we look at and test it at new glass composition where we look at varying this indentation load here. So these are 3 different types of glasses. The reddish points here are the experimental data points. So we have this decrease in the hardness with the load. And the blue here is the predicted from this model that I shown you before. That clearly is not, because it was just trained at these glasses. And yes, there was a load dependence, but typically for each glass, there would only be one load input value. So it fails to kind of capture that. And then the type of physics informed or symbolic regression reasoning that we applied here was, so there is this so-called Bernhardt equation. That was the equation I had on my previous slide here. Essentially can be written different ways, but it's saying the 2 parameters that it goes into is related to the curvature. So how much of an effect is there, and what is the hardness when we go to infinite load or size of the indent there. So what we then did was then to train this machine learning model to predict these 2 parameters with each glass by minimizing a loss function, so between the measured and the predicted hardness. And then this loss is backpropagated through a neural network to learn these optimal weights that minimizes this loss. So in this way, the model is learning this function and relating to the composition and these two parameters. And then we can actually, of course, still not perfect, but we can capture this load dependence here and outperform the purely data-driven model here, and also get a very nice prediction here. So of course you'll notice here the data set is not 3,000 anymore. Here it's like 150 compositions, because here we need to rely on data only in the literature where we have, I think we selected here at least 3 different loads for each of the glasses to be able to at least have the minimal description of this load dependence. So of course it becomes a little bit more problematic to compare because the experimental data from literature are more scarce. Yes. So that was kind of the more macroscopic way of how to use these types of machine learning models to predict a material, in this case, a glass mechanical properties. We've also trying to look at it more like the atomic scale and understand what is going on during fracture and how can we understand the dynamics of those processes. And originally our work into that was motivated by this science paper here, not from our group, but from Frankberg, looking at amorphous alumina, showing that at high strain rates, and if you can make it flaw-free, you can really get a very tensile deformation behavior of an amorphous material. And they ascribed these to structural changes that went on at the atomic scale, these so-called bond switching events. So in this case, it's aluminum and oxygen, and how they change the coordination number. They decrease it, increase it, or they swap one of these neighbors here. So this is also something that had been seen a little bit in other systems. And then what we were looking at was to densify these structures, or to try and understand when and how can we promote this bond switching if this is as this seems to be the important parameter. So here we tried. So again, this is simulation work based on molecular dynamics simulations. At these alumina, we tried to densify them to different amount with the simple idea that we apply pressure, we put the atoms closer together, and they would have more easy to have these bond switching events going on, and that's also what we see. And then I'll come back to that, how we do that in a moment. But then we use this classification-based machine learning to classify these atoms here as either mobile or immobile. And this is some concept also coming from the literature that I will mention in a moment. And what we can see is that we can actually also use it to predict, based on the training, the mobility of these atoms from the static structure before we apply the load, and how that relates to the fracture origin in this case. Okay, so I'll come back to this, because we have been trying to use these for these a class of systems, the glassy systems. These, I mentioned, these solid state electrolytes. So yeah, this applications of glasses where we can use them in battery materials. So to avoid this flammable liquid electrolyte, there's a huge research and development effort to use solid electrolytes, glassy or non-glassy, to enable improved performance here. So two of the issues that we've been looking at, and two of the critical ones, is understanding, of course, the ionic conductivity in these glass materials, and as well as the mechanical properties for these. So of course, when you go from a liquid to a solid, we need to care about that we can still get sufficiently high ionic conductivity in this electrolyte here. And also the mechanical properties become critical, because you can have expansion and contraction during cycling that puts stress in this glass state, and that, of course, as we have discussed, can lead to fracture. So we have an interest in trying to understand some of the proposed or potentially used glassy electrolytes systems, and again with machine learning. So again, this is based on simulations, because when we want to look at the movement, the location, the fracture, and so on, really at the atomic scales, it becomes very complicated, if not impossible, in many cases, to do that experimentally. That probably will happen more and more in the future with more and more advanced techniques. But at least at the moment, we have to look at this with simulation to look at like the positions of the individual atoms. And of course, I won't show you that here, but of course we validate these simulations as good as we can. But of course there are some inherent limitations. Okay, but we're looking at but here are some lithium boron phosphates. So of course lithium as the mobile ion here, and then these boron, these typical network forming networks here. Yeah, and when we vary the composition, as we've discussed, we change the structure. This changes the fracture behavior. And again, what we can see here is that these are stress strain curves, that these are more resistant to fracture when they have a higher amount of these bond switching events, as we predicted. And we discussed before, also the mobility is affected by these structural changes. We have some lithium ions, depending on where they are in this very complicated structure. Some of them are more mobile, some of them are less mobile. So some of them are more trapped in cages, and some of them have a higher mobility. So of course, our interest is to understand why is it, or when is it, that some of the borons are more likely to have these bond switching events that is good for the fracture, and when is it that the lithiums are more likely to be able to more freely or more quickly move around. And if you look at this complicated structure, of course, this is not trivial to figure out. So we mentioned we're using this classification machine learning approach, as I mentioned before, either with a support vector machine or a logistic regression. That is what we've been doing. And this was first proposed not for the mechanics that we are focusing on here, but for other phenomena by Kubrick, Schoenholz, and Liu, and others looking at this, and also a series of follow-up papers. But the idea that we classify the mobility, in our case here, the lithium or the boron, based on the spontaneous dynamics. Typically, we simulate this at 300, so room temperature, 300 Kelvin. And we have some hyperplane to separate these. And then the distance from this, we refer to, or they refer to that in this paper as the softness here. So then we can calculate that for the different atoms, for my boron and for my lithium in the two series of glasses, and we can see how it actually very nicely the probability to undergo bond switching for the boron, and then this is a measure of mobility, this cumulative non-affine displacement, matches nicely with this this softness here. And of course, the interest here is that this is from the static structures here that we get these. So the structure encodes the kind of the features of these when we apply load, when we look at longer time dynamics, change the temperature, these are correlated. So yeah, in this case, as we go up in boron content, we get a higher softness and we get a higher conductivity, and we can see differences also for the fracture behavior of these two types of boron species. So we can kind of, with the machine learning, we can decode what types of atoms are more or less likely to behave, and then of course we can use this to try and design our glasses in a way to get more of the structural features that are good for this behavior that we are looking for in a given situation, based on this really atomic scale understanding. Yes, and then we can look, of course, more into what is causing some of these differences. Maybe I'll skip that, but here with a logistic regression, we have this this weight coefficient here of the classification hyperplane, this WR here, that have the contribution. Yeah, maybe I didn't say that, but we trained that on the radial features, for example, the boron lithium, the boron the boron oxygen, and so on. And we can see what's the relative importance of these for this classification here. So, for example, for the boron, is the boron oxygen interaction that's the most important. For the lithium, is the lithium. We can look at also which neighbors are more likely to give rise for bond switching, and for example, yeah, and what's, if you are away from the equilibrium bond length, you have more likely to move. So with this kind of classification, it can tell us something about, I mean, the overall structure, but you can really also go in and then look at the details, and with our chemical understanding of the glasses, really to understand what is controlling that. And of course, that's all nice, but then of course the huge engineering challenge that is still there is how do we convert this knowledge and design these structures with these features in the right proportions, and with all the constraints that there are as an engineer to in terms of still being manufacturable and price and all these things. The final example here is the related approach. Again, using this so-called softness approach to classify the mobility of these lithium ions. Here, looking purely at the conductivity, but in a different systems. That is not this network type of system, but a more ionic systems where you have lithium ions, and then you have these are thiophosphate. You have 3 types of thiophosphate units. So what's called hypo, pyro, and ortho groups. Yeah, and we make some glasses with varying proportions of these types of structures, and that will affect the rate of the lithium mobility depending on which of these features that you have there. So that is well known experimentally, but what is really governing again this? So as I said, we use this similar approach here, the classification-based machine learning, classify the mobility, softness of these so-called softness of these lithium ions in the different glasses, and what we can see is there's a kind of a clearly spatial distribution here. They are color-coded, and if we overlay that with the structure, these different types of structural units, we can see that there's a clear preference for the more softer lithium to be closer to these so-called ortho group, and the harder lithium ions to be closer to the so-called more hypo groups. We can also see that from the partial distribution, radial distribution function here for the lithium sulfur groups, that these lithium, the harder lithium, the probability is higher to be closer to these hypo groups, and the softer ones are more likely to be closer to these so-called ortho groups. So telling us about why these, or giving some insights into these features, and we can correlate, of course, again to some physical parameters like the local free volume and so on. And we can look at migration, for example, from a lithium site that is starting to be starting position is relatively soft to something that is hard, and understand what kind of structural features give rise to a smaller energy kind of barrier to be overcome, and a higher or a smaller one to be overcome when you move around in the structure around these sites. So this is done using the so-called notch elastic band method, where we look at a central lithium ion, then you remove those around it, and you look at the migration, the energy barrier of migration. You can see that we start from a soft side and go to a hard side. We have a smaller barrier compared to when we start from a hard side and go to a soft side. And again, matching this, how we have more local mobility around the hypergroups and more longer range mobility around these so-called ortho groups. Yes, so I'm coming to the end of my talk. So this was just kind of to summarize a little bit. So of course, what I've been trying to highlight from this engineering view, what we want to go is we need to use our physical chemical understanding of the structure and give them as inputs, at least to some of the machine learning models that we use to improve these mechanical properties. So that is at different length scales, as I'm trying to argue, at short range scale, at medium range scale, and then use that to design these glasses, as we've also been doing, at least at the time, was some of the toughest glasses that have been discovered at this time, using some of these types of approaches. Yeah, I think this final slide here just summarizes what I said. We need to understand the structure at different scales and use a combination of different methods. Of course, thanking the team of students and postdocs in our lab doing the work, and the different funding agencies for the support. Yeah, and again, thanks for the invitation to do this, and of course open to any questions.
Thank you very much, Morten. Thanks for sharing your work. That was very interesting. I open the floor to questions. We have a couple of minutes. In the meantime, I wanted to ask, maybe if you could sort of shed more information about the physics, the machine learning part, especially with regards to symbolic reasoning in 4ML that I saw. Yeah. If you can maybe share some information about this framework and the strategy and the kind of model that sort of constitutes.
Yeah, I mean, so the neural network itself is pretty multi-layer perceptron model, and then we have this so-called Bernhardt equation here, so the typical way in glass science, and what was the kind of the first approaches with machine learning, is that you have the glass composition as input, so that would be the concentration of the different oxide component, and then you have the measured property here as the output, and here the input could also be this load here. And then you would get weights for the different chemical components, and of course, and that way you could train a model. So here we would, as I mentioned, this was coming from this collaborators lab, but here the model was trained to predict these coefficients, these two coefficients that goes into this actually essentially empirical equation, but equation that is describing this load dependence, and then optimizing it on these two parameters that go into the equation, then use that to minimize this loss function between the measured and predicted hardness, and then back propagate that into the neural network, and so it can learn the optimal weights to minimize this loss functions. And this process, we believe that the model is learning this function and relating it to the compositions and then these parameters here. Yeah.
Thank you. Okay, so it's kind of like a learning bias approach. That's what you're going for here. Can you perhaps comment overall about? So it seems like, of course, the tractability and their interpretability of what is being learned is very important for this application, because you care about keeping track of that structure. Can you make a general comment about sort of machine learning and why perhaps you look at the physics-informed machine learning approaches? Which one of their advantages, of course, is that you can maybe go towards maintaining and preserving some form of structure.
Right. Yeah. I mean, again, from the glass point of view. So typically, the issue is that if we just train it just on the and I guess again the information that is typically available, which would be like the components, the concentration of these different oxides. As I was also trying to argue, an oxide is not just have the same structural effect. That will depend on the other types of elements that is there, and really the details of those structural units, and that requires this physical understanding. Unless, of course, if you had sufficient structural data, I think maybe in some cases you could avoid having that, but that is very expensive, and those data are much more rare. So I think that the cheaper way, at least at the moment, is simpler or effective way is to learn that physics in terms of putting biases or learning these interaction that I shown when I showed you these where did I have that structure predictions here. I think so learning these interactions that gives us this good prediction, because it's not really the composition, it's the structural units, and one element like boron is not just B2O3, it can be have 3 oxygen neighbors, it can 4 oxygen neighbors, and as I showed in the end, which of these are there is really crucial for the behavior. You'll get very different kind of properties if you have the 3-fold or the 4-fold. So that's why we need a more detailed understanding. Yeah.
Thank you very much. I also have a third question, but I cannot see if anyone else has any other questions. Okay, then I'll go ahead again. So I'm wondering if you tackle uncertainty in your modeling, given that, of course, your modeling, your data is empirical, and as we know, even with the way you collect data, there's going to be kind of errors there as well.
Yeah, I mean, so the whole curation of the data is really a big thing. So I mean, there's so for example, just these composition that as I said, typically used as input. So many times they will be nominal. I mean, so people have not even measured the composition, so that gives a huge error in that. In some cases, they will be measured. So then, of course, it's always the dilemma: do you include all the data to get a bigger data set, or do you choose those where you are more certain about the compositions, because the nominals and the actual ones can vary a lot. So I would say a big part of using this, of course, especially when we do it in the experimental data, like in the study I've shown here, I think this was trained on 400-500 glass compositions. When we put these restrictions on them, we are in the hundreds, of course, in the limits of where it actually sometimes where it even makes sense to use neural networks, right? But when we go to the more training on the simulations, that of course is a different story, because then we have thousands and thousands of data points. But yeah, I would say curating the data is a key issue in our fields. Yeah.
Thank you so much. Right. Do we have any other questions?
Maybe I can ask a quick question. So just as a curiosity, as far as I understood, we use machine learning. So we have physical models, and we need to use machine learning because sometimes the physical models are not enough. And so, but together, the two combined together, then we have a more general description of what's going on. But I wonder whether sometimes the results from the machine learning can actually help us to further advance the theory. I'm not sure whether this is something you covered. Maybe I missed it, but I wonder what's your opinion on this?
Yeah, no, I think very good point. So I did not mention this maybe explicitly, but I would say actually in these studies that I've shown you more towards the end here, where we kind of looked at, for example, what types of structural environments do our atoms have to give rise to a certain behavior. I think that is the types of understanding that we can use in other physical models, or in just more, if we talk more practical things, just like design criteria. So that type of understanding here in terms of what types of structural environments is needed to give rise to a certain feature, for sure. I think those type of approaches can be very helpful to get physical understanding as well. So yeah.
Brilliant.
Thank you.
Thanks for your question, Andrea. Okay, I think we can wrap this up. If there's no more questions, thank you very much once again, Morten. That was really interesting. And this seminar will be available online, hopefully. And yeah, thanks everyone for joining, and see you for the next seminar.
Thank you. Bye-bye.
Thank you. Thanks once again.